then take the opportunity to examine some object-oriented programming fundamentals that you should understand before you delve into object-oriented design. So first up, what is object-oriented programming? Well, it stresses the creation and interaction of objects. And essentially, objects are things. So we use code to try and represent real-world things. Now, some of the key benefits of doing this include modularity, the ability to hide information. It promotes code reuse, simply because when you write code as objects and have them representing things, well, you can then reuse those things in programs further on down the line. It also improves debugging and testing. One of the reasons for this being that because we attempt to make things so modular, we're very specific about what a class or an object does. So for instance, we would create an object to say represent a shirt in a store. If we have any issues with that shirt object, well, we know that the information or the definition for that shirt is contained in one place. Likewise, any operations that may be performed in, say, in our imaginary store, that too would be managed in one place. So again, if we run into any issues when it comes to debugging and testing, we'll have a pretty good idea, depending on the types of errors that we might run into, where to look to fix these errors. Now, some of the languages that are included under the umbrella of object-oriented programming languages include Java, Microsoft C# and F#. We also have C++, and Perl version 5 is also an object-oriented language. Now, the two key terms that you need to understand are objects and classes. And like I said, objects are essentially things, or code representations of real-world items. And classes are where we create the definition for those things, or the blueprint, if you will. So we map out what the object is or it isn't, what it can or can't do in a class definition, and then we create objects based on that class definition, or the blueprint, if you will. And then we have this concept of abstraction, and abstraction refers to creating classes that are so general and they may contain methods without any particular implementation. So if we think of, say, something like a plant, well, that's a pretty general type of thing. Now we have, flowers and trees and shrubs and grasses, but those things are all plants. So we can take that abstract concept of a plant and actually create a code representation of it, and then from that we can derive specific types of plants. And then there's this notion of polymorphism. And essentially polymorphism means that no matter how much things change or get derived in an object-oriented language, we'll still be able to figure out what type of object that is. Now, another key feature in object-oriented programming languages is this notion of inheritance. Now, we talked a bit about abstract classes. Well, if we were to create an abstract class, say, to represent a plant, then we would derive from that class and create something more specific or more suited to our purposes, like a class to represent a tree. And we would say that the tree is derived from or inherits from its parent class, which in this case would be the plant. And so we can pass on certain characteristics or behaviors through inheritance to child classes. And then we have encapsulation. And encapsulation essentially means that you're only letting people interact with what they need to when it comes to your objects. So you're encapsulating some information, or much of the information, which basically means you're hiding the inner workings of your class definitions and objects from access by users. So now let's take a look at classes and objects and how to create both. So a class defines objects of the same kind, and all objects will share similar characteristics. Say, for example, we're writing a class definition to represent a shirt. Well, you think about it, all shirts share certain characteristics. Or, for instance, plants. All plants share similar characteristics, so we could use a class definition to define what those characteristics are that are shared amongst all the objects of the same type. Then a class also defines what an object is and how it's implemented. So, as we just said, for our plant, for instance, we could specify certain methods that may be associated with the plant. Or if we think about something like a person, well, we can define characteristics, such as first name and last name, and implement those as either data values or maybe even other objects inside our class definition. And you can think of a class as a blueprint for objects. So much like a car has a blueprint or a building has a blueprint defining how it's to be built and what information it contains, what it can do, classes do much sort of the same thing for objects. And then with objects, these are abstract versions of specific real-world things. So we're trying to take something that exists in the real world or a concept that exists in the real world and represent that in code. And it contains data about the specific thing that it represents. So say, for instance, again, it was a car. It may contain something like the make and the model, perhaps the engine size, perhaps the size of the tires that particular car may use. And we can use methods to access or modify the data that our object contains. And we want to do this so that people or programmers, can't go in and change data, willy-nilly here and there without any consequences, because that actually could have consequences for how our programs are going to work. So here we have a class definition that's representing a person, and you'll notice that we've given it the name person, and it contains a single piece of data, which in this case is a string representing the name of the person. We also have a way to access or modify that data, and in this case we have a method called setName, and it takes one parameter, which is the name, and then allows us to change the name. We also have two constructor methods here, and in each case we're creating the name, but however in the first implementation we're creating a default name of John Doe, and in the second implementation we're actually allowing a name to be passed in, and then we set the name on that specific object. So now once we have a class definition created, we can create what's known as an instance of a class. And in this sample here, that's what we're doing. We have a class called people, and inside the main method for this particular class, we're creating a new person named Ted, and we're passing in Ted's name as Ted Jones. So we have the class, which is like our definition or our blueprint, and then we have an instance of the class, which is an object, which in this case here is a person object named Ted, and it contains the information or the name information of Ted Jones. So in this video, let's examine what abstract classes are and look at a couple of code samples to see how they're implemented. So abstract classes are abstract versions of specific real things. So we may create an abstract class to represent a clothing item, because you think about a clothing item, there's many different types of clothing items, shirts and pants and scarves and hats and mittens. Those are all technically clothing items. So even though they're all clothing, each one is very different, but they would actually share a couple of common characteristics. Now, abstract classes can't actually be instantiated, meaning that you can't create an object based on an abstract class. And that's one of the key things you need to remember about abstract classes. is we're modeling something that is so general with an abstract class that it couldn't actually be defined on its own. We need to actually create a subclass or inherit from the abstract class to create a version of it that's specific enough that we can actually create something. Now, obviously, we use the keyword abstract when we're creating abstract classes, and we use that abstract class to define common methods and variables for their subclasses. So, say for instance, we have an abstract class that is representing a vehicle. Well, there are many different types of vehicles. You know, we have cars and bicycles and motorcycles and tanks and planes and so on. But some of the things that they may have in common are, say, maybe things like, if they have wheels or not. What size are those wheels? Does it have an engine? What's the size of the engine? So common things that are spread across all the subclasses. Now, if we look at this code sample here, we have a Java code sample, and it's an abstract class that represents an attendee. So we think about a conference, and say we're writing a program to represent the different aspects of the conference, and one of those things that we need to represent is somebody who's actually attending the conference. So attendee, in this case, is fairly general. We could have attendees that are, say, delegates. We could have attendees that are presenters. We could even have, say, attendees that are actually people working at the conference to help other people. So attendee is a pretty general definition, if you will. But some of the things that might be common with attendees are the names, the company that they work for, phone numbers, whether or not they're vegetarian, in case we're supplying meals, and the number of events that they're attending. And you'll see in the methods that I have public abstract int attending events. So I've created an abstract method that a subclass that is derived from the attendee class will implement. And then I have a quote-unquote regular method, if you will, that is a Boolean, so it's going to return true or false whether or not they're booking a specific event. But again, the idea is that you're general enough that these methods or variables could apply to all of the subclasses of attendee. And then on our next page, we have a delegate. So a delegate is a type of attendee. So public class delegate extends attendee. So we have to create a subclass to actually come up with something concrete enough that we can create the attendee. So here we're introducing some new values. So Boolean payment received. We've got a constructor method here. And the constructor, you'll notice, is passing in things like the name, the company, the phone number, and whether or not they're vegetarian. And if we look at the previous sample, you'll notice that we have, member variables are name, company, phone number, vegetarian, and is attending. And you'll also notice that we've got the abstract int attending events. And again, in the subclass is where we're actually implementing that method. So we're defining that method because how it's implemented could be unique to the particular subclass of the abstract class that we're working with. So again, we have our abstract class, which is a very general definition, and it contains the methods and the information or the data, if you will, that could apply to all types of attendees in this case. And so we have a delegate class that is extending attendee. So we're creating something concrete enough that it can stand on its own, but it's also a type of attendee. So hopefully this gives you a good idea of how you might use abstract classes to model something fairly general and then create a subclass based on that to get into a version of the class that is specific. So in this video, we're going to look at the object-oriented programming concept of encapsulation. So defining what it is, what its benefits are, and then we'll look at a code sample that implements this concept. So encapsulation is essentially the combining of associated variables and methods within the same object. And the use of data encapsulation is in contrast to procedural languages, in which the data and the code that acts on that data are treated as separate entities. And one of the benefits of encapsulation is that the data contained in the object's variables can also be protected from unauthorized access. And we can ensure that it's only accessed by using appropriate methods. So we can set up these methods to change only what we need to, or see the bits that we only want to show to specific people. If the data was, say, declared public right from the outset, well, that doesn't stop anybody from maybe changing parts of our object that are key to the inner workings of that definition. So it could really have a huge knock-on effect. So we need to maintain tight control over how that information is accessed. So by accessing data through specific methods associated with the object, this encourages what is known as loose coupling. And this is basically what happens when a class only allows other classes to gain knowledge about its inner workings through the exposed methods. And one of the benefits of this is that if we need to make a change to the inner workings of that method, well, so long as we don't necessarily change, the parameters of the return type, these other classes can still interact with it in much the same way. Now, if the class could freely interact with all the variables and the methods in another class, that's what's known as tight coupling, and it's not really recommended because, as you can suspect, this could be very prone to error. Now, in this class definition, I've got a person class defined, and you'll notice that I've got a variable private string name. And I've made that variable private because I want to restrict access to that specific piece of data. And you'll notice I also have the constructor methods in here and a method for setting the name. So that's a public method, as are the constructors. So we're controlling how people outside this class definition can interact with that object. So we don't want people just being able to change that name value without going in through a method. So in this case here, they have to go in through either the appropriate constructor or use the set name method. Now, right now, we're just accepting the name and automatically setting the name property to that. But we could also introduce some logic here to verify that, the name is of a certain length, or say we're setting an age, for instance, we could set a specific age range and so on. So again, encapsulation, we're grouping all the relevant bits and pieces in one place, and we're also restricting how those bits and pieces can be accessed by allowing people outside this class definition to only go in and modify those bits by using public methods of the object. So let's explore some of the concepts around inheritance, and we'll follow that up with looking at a couple of code samples that illustrate how it works. So when we talk about inheritance in object-oriented languages, what we're basically saying is that we can define new classes based on existing classes. And when we do this, we have what's known as the superclass, which is the existing one or the parent, and the child class, which is the one that we're creating based on the existing one. And when we think about, if it's a good fit to extend one class from another, ask yourself, is this class a type of that superclass, or would it be a case where that superclass has a version of that object as part of its definition? So if we think about employees, so a type of employee, for instance, might be a janitor. So we could say, well, a janitor is an employee. However, we couldn't say that an employee has a janitor, or vice versa. But if we think about, say, something like a car and a vehicle, well, a car is a vehicle. Likewise, a car has an engine, or it has an engine. So we may create an engine object, but that engine object would not be derived from a car, for instance. And what inheritance allows us to do is actually inherit methods and data in the superclass. So anything that we may have set out in our superclass definition for, say, our vehicle, well, that would get passed on to the child subclass in this case, or the child class, which would, say, be the car. You know, child classes can create their own methods, but they can also do what's known as overriding existing methods. So basically, they take an existing method and create their own version of it. But one thing to look out for here is that it requires the same number and type of parameters to be passed to it as the method it overrides. Otherwise, this is what's known as overloading. Now, lastly, we can't override a method that's marked as final. So essentially, we've said in the superclass, nope, this is it. This is the only version of this method I want to exist in this hierarchy, so we can mark that as final. Now, we've got a few different types of inheritance. So simple inheritance, easy enough. A janitor extends from an employee superclass. So a janitor is a type of employee. We can also have multi-level inheritance. So we can have employee, which is pretty general. A janitor is a type of employee. So that's, again, kind of general. But then we might have a specific type of janitor. So a basement janitor in this case. So as we get further on down the chain, if you will, we're getting a bit more specific with the type of employee that we're creating. So again, employee, pretty general. Janitor, a bit more specific, and then more specific still, a basement janitor. Then we have what's known as hierarchical inheritance. This is where we have a setup that's, say, similar to a family tree. So we got the base class for employee or superclass. Well, from that we can extend janitor, okay, which is a type of employee. But now you think about an electrician. Well, an electrician is a type of employee, but it's not a type of janitor. So we extend that from the superclass in this case. And we could also add, plumbers, professors, whatever you can think of that would be an employee that's not a type of the other ones in the hierarchy, we could extend from the base class. So in this example, we have a base class or a superclass called attendee. So we're modeling an attendee to a conference. So we're pretty general with this one here. But we've got the name, the company, the phone number, whether or not they're vegetarian, the number of events that they're attending. We have a constructor, and then we have a method called attending events, and that just gives us back the number of events that they're attending. So now if we think about a delegate, okay, so a delegate is somebody that's coming to the conference, versus, say, a presenter, which is, he or she is showing up and they're going to be presenting at the conference. So delegate extends attendee. So a delegate is a type of attendee. And we're adding an extra variable here, so a Boolean value for payment received. We're also including a constructor, which accepts a name, the company, the phone number, and whether or not they're vegetarian. We're using the keyword super to invoke the constructor that is in our attendee class, because delegate is a type of attendee. So anytime that we have a child class that has a constructor, we need to invoke the superclass constructor as well. And then we're setting our extra variable here, payment received equal to false. And then we're adding in method for simply booking the event. So again, we had a kind of general base class, if you will, for all attendees. Then we created something a bit more specific to represent delegates that are coming to our conference. So let's take a look at the concept of polymorphism and how it applies to an object-oriented language, specifically Java, and then follow that up with a little code sample that illustrates how it works. So polymorphism is basically the ability to use an object as if it were an object of its superclass while still using its overridden methods. And inheritance and overriding form the basis of polymorphism. And what this allows you to do is implement subclass-specific versions of a superclass method. And you create subclasses by extending superclasses, and you also hide superclass variables. Now what you can do is you can override superclass methods and add specific functionality to them. So functionality that is specific to that subclass. Now here we have an example, say where we have an animal superclass. And we also have a dog and a cat, and they're both types of animals. And let's say, for instance, that the animal superclass has a speak method. Well, it would make sense to implement that speak method in both the dog and the cat subclasses or child classes. But what each of those methods says for the dog and the cat, well, it's going to be two different things, right? Because a dog barks or says woof, and the cat would meow. So this is where polymorphism comes into play. So when you compile these classes or these objects at runtime, you'll be able to refer to the speak method, and the language would figure out exactly what specific speak method you're referring to. Is it the speak method that's in the dog or the animal, or the cat versus the animal, or the dog or the cat? So to follow that up with a code example that will hopefully make things a little clearer. So we have our base class animal, and it has a speak method. And all we're doing here is just printing out sound. Then we have dog that extends animal, and it has a speak method. So dog is overriding the speak method in the animal superclass. And what it's done is that instead of just saying sound, it will now print out woof. Likewise, cat extends animal, so we're overriding the speak method there as well, because a cat makes a very specific sound. So system.out.println meow. Now, where polymorphism comes into play is that what it boils down to is that the engine will understand which speak method we're referring to based on the type of object that we're using. So if we have a dog object that we call speak, it'll find that version of the method and use it. If we have a cat object and call speak, it'll know we're talking about the cat. If we just had a generic animal, it would know that we're talking about the speak method that's defined in there. So essentially, polymorphism is the way that an object-oriented language like Java can keep this all straight and know which method to call when. Thinking about object-oriented design, what is it exactly that we mean? Well, object-oriented design concerns itself with the analysis and design of objects and products. And at the analysis phase, essentially what we're doing is we're sitting down, we're looking at a problem, and we're identifying the specific parts of that problem. So we identify the problem to solve and the key components. In the design portion of that, we apply the findings from our analysis, and then we attempt to develop blueprints or models. So we're sketching out a plan, if you will, for how we're going to attack this in code. Now, in object-oriented programming, or when we get into actually coding, here's where we implement the plan that was laid out during the design stage using whatever programming language we were using, so whether it's Java or C#, C++, and so on. Now, object-oriented design stresses some of the key advantages of object-oriented programming, and these include modularity, so having things serve a very specific purpose broken up into modules. This notion of information hiding, so only letting other classes and objects either view or modify information through methods that you have set out yourself or defined. Promotes this notion of code reuse. So this also touches on the concept of inheritance in object-oriented programming. Basically, we don't need to reinvent the wheel. Say we have a car class and we want to create a more specific version of a car. So say we have just a general car, and then we want to have a more specific car, say like a smart car, or even just a specific model of a car. Well, we don't need to reinvent the wheel. We can extend a new class from the existing car class and add what we need to. So we're reusing that code. Also, this notion of abstraction, so taking real-world things and trying to model them in code. It also promotes improved debugging and testing, and again, this ties into this notion of modularity and code reuse. So because things are broken up into modules and we're attempting to reuse things as much as possible, it'll streamline things further on down the line. If we run into any issues, we can figure out where things have gone wrong, hopefully, a bit more easily. Now, object-oriented design can include the modeling of classes and systems, and to do that, we'll use what's called Unified Modeling Language, or UML, which is basically just a graphical representation of things like objects and classes, the different states that these objects are going to be in, so use case diagrams, things of that nature. And there's a few different tools that we can use. We have Visio, that's from Microsoft. There's also an open source tool called UML that you can use. And both NetBeans and the Eclipse IDEs have plugins that you can install to do your modeling right inside those editors. Now, there's also certain design principles that we can implement as part of our object-oriented design, and they include things like solid, grasp, dry, and CRC. So let's talk a bit about what Unified Modeling Language is, its key aspects, and how that applies to object-oriented design. So Unified Modeling Language concerns itself with modeling objects, their attributes, what they can do, their operations, and their relationships with other objects. And we can also use it to model the dynamic behavior of the system by showing collaborations among objects and changes to the internal state of those objects. Now, there are different types of diagrams that UML utilizes, and they're divided up into three broad categories. So we have structure diagrams. These are the things that are being modeled. So that would go back to, the objects, the attributes, what they can do, their relationships with other objects. Then we have behavior diagrams. So that's the behavior of the system. And then we have interaction diagrams, and this is the sequence or the program flow of the system as its whole. Things like following data throughout the program flow to see where it goes, things like that. There are a variety of UML tools that you can use. These include Microsoft Visio. It's a very nice editor for creating UML diagrams. UML is an open source free editor that you can download and create UML diagrams as well. And there are also plugins available for NetBeans and Eclipse. So you can install these plugins, and if you're using either of these IDEs to, say, program in Java, well, you can map out or model your object-oriented design using UML right inside those editors. And then lastly, you can even sit down with a simple piece of paper and use a pen, and using UML diagrams map out what you're doing. But obviously the advantage of using an actual editor is you can save that file, and it's a lot easier to pull that up and just share with other developers on the project, instead of photographing a piece of paper and handing that around and saying that, okay, here's my use case for the project that we're about to start developing on. So let's explore some of the key aspects of UML use cases, and then look at how to create a very basic use case in Visio to represent how a user may interact with a bank. So use cases are just graphical representations of the system or solution that you're attempting to model. And our takeaways from this is we'll have a visual representation of the key behaviors in that model and also the key requirements. And use cases consist of actors, which are the key players or the key objects in this model, if you will. The use case, what those actors can do. Actors are then associated with use cases or their behaviors or operations, if you will, through associations. And they can also use subsystems or components. And these are just independent or behavioral units in the system. So things like classes, components, and these can be used to represent a variety of independent things. So I've switched into Microsoft Visio Professional, and it's a very good modeling tool for a variety of different types of products, but specifically it can be used to create UML diagrams. So to begin with, I'm going to go into File, and then into New, and I have a few different options here. You'll see that some of the more common templates are already showing up here, but let's assume that the one that we need isn't showing up. So let's just go into Categories, and if I scroll down, you'll see that there is a Software and Database one, and then from here I can find my UML use case, and so we'll select that, and we'll just we'll say metric units for now. Okay, so we're presented with our modeling area, and you'll see over here on the left hand side that I have actors, I have use cases, and I have things like subsystem and association. So a common use case that people use to illustrate this concept is, say, a bank machine or an ATM. So now the machine itself would actually be considered a subsystem. So I'm going to click and drag the subsystem over onto my modeling area, and I'm going to increase the size here so I can view that a little bit more easy. And so we'll just call this one bank machine, and that's going to be our system. So what interacts with that system? Well, that would be one of our actors here, and I'll edit the text here, and we'll simply call this bank client. All right, so what are some of the different things that this bank client is going to be able to do? So let's make this a little bit bigger. So, whoops. Well, you think about a bank machine. Okay, so some of the things that we can do are, most importantly, we can withdraw money. We can also deposit money. We can check our balances. Line that up. So we'll say check balance. I can also transfer money from one account to another. Okay, so we've got, I guess, four of the key things that a typical bank client would do. Now, I'm not going to get into things like paying bills and that because it could get very complicated, but you could also build those out. So now I want to create an association between the client and that particular use case. So I'll drag and drop an association here, and you'll see it connects to the bank client. Then I grab the other end and drag that to the use case. So withdraw money. And I'll create another one. So deposit. And whoops. There we go. Connect that to there. So check the balance. And another one for transferring the money. So now I have a representation of the different use cases or the different things that the bank client can do in this particular system. But now let's not forget another key actor in the situation, which is the bank itself. So I can add another actor and put them over on this side, and we'll give them a name. And we'll just call them bank, the ever anonymous bank. And so you think about, okay, so what are the things that the bank can do to my account as well? Well, they can actually do all of these things. So I can create an association over here, and apply that to the different actions, and then I could continue on and do this for the rest of the use cases that are part of my bank system here. And so I'll just quickly do that. And then in a system like this, or you'll also have, say, somebody who performs maintenance and stocks the cash in the machine. So we can actually introduce another actor here, and I'll just maybe call them technician. Okay, and we'll move them a little further on down out of the way. And so the thing that they can do is, we'll just say they can perform maintenance, or we'll just say maintenance. And this would include things like service the machine, replenish the money, and so on. And we'll create an association here, and then connect that to their specific use case. So now that we're done, you can sit back and look at the different actors in your system, and the different things that those actors are going to be able to need to do when you start actually speccing out the different methods and so on that would be associated with these different objects. So let's look at what a UML class diagram is and how to create a sample one to, say, model a basic employee class. So I'm in Visio, and I'm just going to go into New, and from here I'm going to select the software category, and you'll see that I have a variety of UML charts that I can create. And so I'm going to select UML class right here, and we'll click on Create, and I'm going to increase the size of my work area just a little bit here. Okay. So when you're working in UML, or I guess in object-oriented design, it's a good idea to model out your classes, their relationships with other classes, before you maybe even get into thinking about creating the code for those. So in this case here, I'm going to create a class diagram to represent a basic employee class. So to create the class diagram on our left-hand side, I just select the class diagram, drag it on to my space. And right away you'll see that I have class name and then member name. And here is where I can add the members, whether they be properties or methods that this particular class can perform. So the first thing I want to do is change my class name, and I'll just call that employee. And I'm going to add a couple of more members to this, so for both the properties and the methods. And you'll see I have a separator here. Typically you'll have your properties / attributes on the top part of the diagram, and then the operations that they can perform below. Alright, so let's give these a few names. So if we think about employees, well, we'll want to know their first name, their last name, and I probably want to add another one here to maybe represent the employee ID, and I'll drag that down a little bit. So call that EMP ID. Now for the operations, well, if we think about what we want to be able to do with this class, well, we want to create new objects based on that. And we'll probably also want to be able to find out the first name, last name, and employee ID. So I'm going to add a few more into here. And so the first thing I'm going to do is add the employee there. So if we're thinking about Java, constructors name the same as the class. And so let's maybe call the next one EMP get ID. So we'll retrieve the employee ID, and then maybe get last name, and then get whoops, first name. Now, this is a very general class, and in fact, it could probably be abstract. So we can actually create more specific versions of the employee class. So let's say that we're actually representing employees at a power plant, for instance. Well, we can actually add a couple of subclasses in here below, and I can use this inheritance line to indicate that there is a, get in there, relationship between this parent class or superclass and you'll find that if you're using, I guess it really doesn't matter what tool you're using, these can be a little bit tricky. So we'll move this one down and we'll add another inheritance connector for this. Go up to the same spot. Okay. There, let's just try to mimic how the other one looks. And I may not be able to do that without getting frustrated. Okay, fair enough. So we could have our janitor class here. And the janitor is actually going to share some of the same members as its parent class. So we can just copy and paste some of those right into it. And it may actually introduce some new ones, and we can also share the same behaviors as well. So we could actually copy and paste those over. Now, for the next one over here, I'll come back to that in just a sec, we could call this an electrician. And again, the electrician would share a lot of the same information that the employee would have, so things like first name, last name, and employee ID. So I can copy those, paste in there, and I'll move this one down below. And maybe I'll introduce a new one and call that specialty. Oh, move that up. There we go. So what specific type of electrician are they? And then over here, I could introduce something specific to this particular employee. So again, thinking about specialties here, janitor type. And it would probably be more realistic to call this one electrician type. So what specific specialty that they have. And I'm not going to introduce any new behaviors at this point, so I can delete that. So here you can at least get an idea of how useful a tool it is to design your classes in a modeling tool like Visio using UML before you sit down and start coding, because it gives you an area that you can map out the different objects, their relationships to one another, really think about what you're using for attributes and the methods. And again, it's really good to get a lot of this out of the way before you sit down and begin writing even your first line of code. When you're using UML to help you model and design your software solution, one of the things that you should look at are what's known as state charts. And basically state charts allow you to look at the different states that a specific object may be in during a certain process. So if we think about the example that we have here where we have a bank client, and they're interacting with the bank machine, and they're performing certain operations like withdrawing money, deposit money, and so on. Well, there's going to be different states that occur during the process of whether or not they can, say, withdraw any money. So if I go into File and New, I'll go into my software category, and you'll see that there's a template already here for Uml State Machine, and that's the one that we want. So I'll open that, and you'll see it says use the state machine to create graphs of states and transitions that describe the response of an object to outside stimuli. Okay, so we'll create that. It'll just take a moment. Now typically when you're modeling state charts, you'll have an initial state and then a final state, so your destination, if you will, or how things are when everything has completed. Now, in between here, you'll have transitions and also states, and we can drag and drop those specific states over to our chart. So if I move my mouse over the initial state, I have the option to add a blank default state or a state with some internal information or internal behaviors here. So let's just add a blank one right now, and I'm going to move this just down here. And so you think about the different states that this process might be in. So somebody comes up to a bank machine, they want to withdraw some money. Okay, so the first thing it's going to do is verify that the card is okay. And we've got a choice here now that, okay, if the card is okay, we're going to proceed to a certain state, and if it's not okay, we're going to proceed to another. So I can add a choice into here, and I'll just put that right below. Now, you'll see that it didn't actually add a connector here, so I can go and insert a connector, add that here, go to here, and I'm going to add another substate to here, and we'll just simply call this one card OK, and I'll add another one to here, card not valid. Now at this point here, if the card is not valid, we could actually add a connector here to take them right to the end state and then kick them out of the process altogether. But if things are okay, we could include a transition to another state that would be to perform a transaction on the account. Now, depending on what type of transaction, I'll move that over here so it's a little easier to see. Or actually, maybe I'll move my, there we go, final state to here. We could then, verify, okay, are there enough funds in the account? Can they withdraw, transfer, and so on? We could also add those, all with the end goal of getting to this final state. Now, I've really just scratched the surface here, starting to run out of room a little bit, but hopefully you can get a good idea that by using UML state charts, that are a very useful tool for sitting down and thinking about the different states and the different things that you're going to need to consider as you work your way through a specific software solution. So let's use Visio to explore what an activity diagram is, and then create one to perhaps model what happens when a bank client wants to withdraw money. So here we have a use case diagram. We're outlining a couple of clients here. We've got the bank client, the bank itself, and the technician. And some of the things that the bank client can do are withdraw money, deposit, check their balance, transfer money, and so on. So we can use an activity diagram to essentially map out what is going to happen when this client goes to their bank machine and they want to withdraw money. So we can actually go into File and New, and we can select UML activity, or we can go into the suggested category for software, and we'll go and find it right here, and you'll see that it says an activity diagram illustrates how a system accomplishes its goals. Okay, So we'll create that. All right, so we'll use what's known as a swim lane to represent the different actors, if you will, or the different participants. And add that one there, and add this here. Now, I'm going to make those a little smaller, and this will actually automatically resize if we need to. And we'll increase the size here a little bit. All right, so we can give this a title, and we'll just name this Withdraw Money, because we're trying to essentially model what's going to happen when the client is going to withdraw money. All right. And you'll notice that it automatically expanded this and put a few more lanes in here. Well, we don't actually need those, so I'm going to get rid of those. So we'll name this first one Bank Client, and that's to represent the client. We'll call this Bank Machine, and we'll just simply say bank. And by bank, we really mean the institution or the software on their end that's going to let us know if we can withdraw money or not. All right, so we'll start off with our initial node, and we'll put that into our bank client section. And we'll also have a final node, and I'm going to make that a bit smaller here, and I can put that down in here. And so we think about, okay, so what is a client going to do? So the action, which we'll put here, is going to be insert bank card. All right. So when that happens, the bank machine will then have to respond to that. And we can actually, if we select this and we go in this direction, we can put an action in for the bank machine, and we'll put it in here. And you'll notice that it's dragging across. And I can resize that. And we'll just simply say respond. And so you think about the way that a bank machine works. We would then actually add another action here, right below it, which will be ask for PIN. And then that would then go back to the client, and they would provide the PIN. Now, once we get that PIN, we can add another action which would actually get sent over to the bank. And the bank's going to validate PIN. And when it does that, this is when we can introduce a decision node, which we'll put right underneath. And I actually shouldn't forget my connectors. Put that in there. And same for here, I should put my connector in. Okay, so we can see here, okay, insert bank card. The bank machine is going to respond. It's going to ask for the PIN. It goes back to the client. They provide the PIN, which then gets sent to the bank to validate the PIN. And I can make this a little bit bigger because I need to add a few more steps here. Now, I'm going to move this down near my bottom here. I can then actually include another action here. And what's going to happen is, in this case here, if things are okay, we'll let them actually request those funds. And we just put a little connector here. Fair enough, put that up a little higher. And we'll say withdraw request. And I could actually then add another action here and put it over here and make this a little bit bigger. Now here's where we're starting to get a little bit more complicated. So essentially what's going to happen is it would validate the pin. If it's okay, then we can respond to this withdraw request, which would then go to, say, a check balance, which could then branch off into another decision, which, okay, if the balance is okay, then we'll let them withdraw the money. So hopefully you can get an idea here of the use of these types of activity diagrams. So you think something even as simple as going and requesting money from your bank machine, when you sit down and map it all out, there actually are a lot of moving parts that may be involved in that final decision to whether or not let the client have the money. So a UML activity diagram is a good way to visually map that out so that you can design your response properly. So let's explore the dry or don't repeat yourself principle of object-oriented design. So dry or don't repeat yourself essentially goes back to the notion that every piece of knowledge must have a single, unambiguous, authoritative representation within a system. So the problem is oftentimes there will be duplication of logic in objects used in programs. And this could be widespread amongst various objects and classes. It could also be methods within a single class definition where you have methods that are repeating the same calculations over and over again. And so your solution to this is to write reusable modular code. So one of the notions of object-oriented design is that it attempts to be very modular, meaning that everything has a very specific single purpose, and then you can reuse that component over and over again as you need to. So write once and then call it when it's needed. And so we can use interfaces and methods for this specific purpose. Now, dry is achieved through proper planning, so it's always important to design your programs before you start writing the first line of code. Now, a good example of this is actually CSS styling. Oftentimes, people may be applying the same look and feel to various web pages, and if they were to repeat that code in every page, well, that's quite inefficient, and if you need to update the look and feel, then you need to change code in every page. However, if you separate that out into an external style sheet that each of those pages refer to, well, then it's actually become very modular at that point, because all you need to do is update the styling in one specific document, and those changes would propagate out to the different pages on the site. Or if we think about, say, our shape class hierarchy here, we could have code inside our shape base class that does not get repeated in the rectangle, the square, and the oval, and the circle, just simply because of the fact that we can consider squares and rectangles to be shapes, as we can consider circles and ovals to be shapes. And you can thank polymorphism and inheritance for that. So base class methods are inherited by those subclasses, so we're not repeating code unnecessarily. So let's examine what class responsibility cards are and how you can use them to help aid in your object-oriented design. So a class responsibility card, or a CRC, is proposed as an alternative to UML use cases, although oftentimes people will probably use a combination of both if they employ the CRC. So essentially what you're doing is you're documenting the responsibilities and collaborations of a class. And so you'll examine, what the class is, what a class can do, and what the class knows. And so with that information, you would create a class responsibility collaboration card, or a CRC. And so you can even just take recipe cards, for instance, or, the little cards that you use for speeches. And so at the top, you would typically put the class name, on the left-hand side, the responsibilities, and on the right-hand side, the collaborators, so classes that it interacts with. So for instance here, we could have a CRC for a customer and another one for an order. And so the customer CRC, we have the responsibilities of, okay, it can place orders, it knows its own name, its address, its order history. Perhaps we could add, okay, it knows its customer ID. And then it collaborates with the order class or order objects. And then the order class is responsible for knowing its order date, the items in the order, the delivery date, it knows the taxes, and also the order number. And then it in turn would collaborate with order items. And so once you had your cards filled out for the different objects in the system and how they were interacting, you could then maybe turn that into a use case diagram if you wanted, or simply sketch something out on a piece of paper. But the idea is that you can use CRCs to help map out the different objects and their responsibilities and how they interact with one another before you start actually building the program, to give you a good idea of the design of that program.